Welcome to the AAA tutorial on open loop dynamics. The open loop dynamics are found under the dynamics module and the dynamics submodule. Then it's split over longitudinal, lateral directional and the roll coupling, and today we will go into the longitudinal and lateral directional modules. The longitudinal open loop dynamics are split further into transfer functions, flying qualities and sensitivity. Let's first take a look at the transfer functions, and we can see that the transfer functions are available for any type of longitudinal control surface that is present on the aircraft. For the Cessna 172 example we are looking at today, we have an elevator and we can also select the non-transfer function, so basically not depending on any longitudinal control surface. Let's look at the elevator first. Here we see that the elevator transfer function, the inputs basically come from the stability and control module. So if you see any missing inputs, please revisit the stability and control module to calculate these inputs, or use the go-to buttons. Then let's take a look at the outputs. And there we see the derivatives that are required to calculate the transfer functions, as well as the coefficients, the short period natural frequency and damping ratio, the phugoid natural frequency and damping ratio, and we see there's a third mode and there's some time constants. The time constants are empty in the case when there's no real roots in the calculation. So if you hit calculate, you'll see also that that note pops up that there are no real roots in the characteristic equation, therefore no time constants exist. Then if you hit OK, you'll see that the transfer functions actually will show up. Here's the transfer function of speed with respect to the elevator deflection in polynomial form and in factored form. If you hit OK, you can see the transfer function with respect to the angle of attack and the elevator deflection. And the last one is the pitch versus elevator deflection. You also see that even though that all the inputs are present, there's still some output left undefined. And that is also explained in the theory. So in the theory, you can see the longitudinal transfer functions being explained in further detail. So you see all the equations that are being used. And if you scroll down, what you can see is all the way down, there's a couple notes. So here, the longitudinal stability is determined by the characteristic equation. For an airplane with two complex pair roots, they are cast in the following form. So the one with the highest frequency is the short period, and the lowest frequency is the phugoid mode. If there's one pair of complex roots and two real roots, there's a third oscillation from placing the complex pair in the same form as the short period and the phugoid. The real roots are cast into the time constants, which are as follows. So then we see that there's a time constant, but also for airplanes with four real roots, all are formed into time constants. Only one of the three possible combinations will result in output. So there's either two complex pairs, there's one complex pair and two time constants, or there's four time constants, the other output variables are left undefined. The same will actually apply here in the non-transfer functions. So let's look into the lateral directional transfer functions, and then after we will step to the flying qualities. In the lateral directional, we have the same structure, so you can see there's a transfer function. And here for the Cessna 172, we're going to select our lateral directional control surfaces, which are the aileron, the rudder, and none. And they basically work the same way as the elevator. You see a lot of the input is stability and control related. And using the stability and control derivatives, we are going to calculate our output for the aileron. So here on the bottom, we see a very similar output. So you see some of the derivatives, and you also see some of the coefficients here. You also see that instead of phugoid and short period, we're looking at Dutch roll, and you also see some time constants. So let's hit calculate, and once again it looks very familiar as the elevator. So you see the side slip angle with aileron deflection, the roll angle and aileron deflection transfer function, and the change in heading angle with aileron deflection transfer function. The rudder wheel look very similar, so let's go and visit this module. We can hit calculate and we see similar messages popping up, but now with rudder deflection. Let's use this into flying qualities. So if we go to longitudinal, let's go to the longitudinal flying qualities first. You'll see here that modes of aircraft are checked against the specifications. If there's no FAR 23 or FAR 25 specifications, the military specifications are used. Then you see here the input is basically the natural frequency and the damping for both the short period and the phugoid, and also the vertical acceleration by a change of angle of attack. Then if you hit calculate, you can see here there's basically a calculation in the steady state normal acceleration. There's a time to halve the amplitude for the phugoid, and you can see some levels here. And these levels are all explained in the theory. So here we can look at, for example, short period mode requirements or the phugoid mode requirements. So let's take a look into the short period mode requirements. We see here military standards are being used. So what you see here is that it's basically looking at a damping ratio for the short period. So in flight phase category A, B, or C, you have different requirements. And to reach level 1, you need at least 0.35 damping ratio in category A. If you click on these, you will see what these different flight phases actually are. So here you see category A, category C, and category B. And for us, we're looking at a cruise condition here. So we're looking at the cruise, the category B level requirements. We can do the same thing here for the lateral directional flying qualities. Once again, the same message you'll see. And also you can see that the flying qualities are split over roll performance and spiral Dutch roll. Let's look into the roll performance. So here we see our roll performance, all our inputs are present, and we can hit calculate. And we can see that we have level 1 for roll performance for this aircraft. Visit the theory to find the different requirements for roll performance. Next is the spiral Dutch roll. And here, if we hit calculate, you can see that using the inputs, we actually have level 3, but also requirements that are not met and requirements that are below level 3. So using the theory, you can find reasons why this is below criteria. So one thing I observed already is that the Dutch roll mode damping ratio is negative. So how can we fix that? Therefore, we can look into the sensitivity module here. So the sensitivity basically will show us how particular parameters can change and what impact that will have on the damping ratio. So let's, for example, take a look at CL beta. So here we basically ask to plot a minimum value for CL beta and a maximum value for CL beta. So let's say we want to look between 75% and 125% of our original CL beta. So if we plot this, we can basically see what our damping ratio is for different values of CL beta. So let's change our axis so we actually see our damping ratio. And here we see that by decreasing CL beta, or basically like if it making it less negative, so you basically increase the value, you can see that the damping ratio slowly becomes more towards 0. So let's zoom in a little bit here. So let's go to just view the damping ratio. And here you see that you might need to change your value of CL beta to change your damping ratio. You can also look at the other parameters here. So you can also look at CY beta, CN beta, or any of the other parameters to see what the sensitivity is on the damping ratio. That concludes the tutorial on the open loop dynamics. Let us know if you have any questions or suggestions for new tutorials.